Going live, just I need to mute on the other side. It's about 30 seconds delay usually. Going live, just I need to mute on the other side. It's about, yeah, how do I say? Okay, I think we're almost ready. I usually go by my official timer, which is my iPhone. You can hear me okay, right? William? Well, no. All right. So it's time for, once again, thank you everybody to join in on the online SPICE-SPIN+X seminars organized here by the Spin Phenomenon Interdisciplinary Center that I lead together with Angela Wittmann, again, University now and Duisburg, in collaboration with the SPIN+X Collaboration Research Center led by Martina Schliemann and Burkhard Hillebrandt in Kaiserslautern and Matthias Chloe here in Mainz. This is a Zoom seminar, as you all know by now. Please feel free to write in the Q&A during the talk or in the chat now. It's also available to the panelists to questions that you may have. With this, I would like to introduce today's young and upcoming star in our field of fast optics, magnet optics, Will Windsor, Yoav, William Windsor, at the TU Berlin. He obtained his master's in Tel Aviv University in 2012 and his PhD in Zurich in 2017. And he's well known for the ultrafast laser-induced variations in the femtosecond and X-ray diffraction experiments in condensed matter, and has had a very good impact in the field already. And I gave a wonderful seminar in a recent workshop in SPICE. And with that, I will stop sharing, and I will ask you, please go ahead, Will, and start your seminar whenever you're ready.
So thank you for this very nice introduction. Can you hear me?
Yeah, I can already hear you perfectly. Go ahead.
Thank you. Thank you for this nice introduction. Thank you for inviting me. Today I'm going to talk. I need to make this little panel here smaller. So today I'm going to talk about our work on FGT, which is a 2D ferromagnet. I'll talk a bit about what that means a bit later. I'll start by saying that I work for TU Berlin. Most of our group is affiliated also with the Fritz Haber Institute in Berlin. Our labs are there. I'm going to give a relatively complete, but I don't know, it's going to be a bit like Swiss cheese, this talk, because everything I'm going to be talking about is not published yet. I've kind of omitted certain things in agreement with colleagues who are involved. But I think that because this work has a relatively wide breadth, it's still going to be, I guess, interesting for everybody, or at least for many people. So, why is it not working? Hello? Of course, I'm having trouble now. So this talk, oh man, this Zoom thing is in my way.
Okay.
That's new.
Go ahead, take your time. It's no problem.
It's okay. We'll make it work. This is going to be a talk about 2D materials, specifically 2D ferromagnets, which is a very wide field that a lot of people are working at it over the last 10 years or so. I'm going to give a little bit of introduction about that. And the other side of this talk is that it is an ultra-fast experiment, or it's about many ultra-fast experiments where we use a very short laser pulse to excite a system and watch how the system evolves following that photo excitation. So what you see here is this kind of picture that is heavily used in these kind of experiments where we have, we sort of imagine our material as a collection of different heat baths that are coupled to each other with these kind of coupling constants or coupling terms. And we usually probe one of these degrees of freedom, and then we can describe how it evolves following the photo excitation, like shown here in this picture, which I will also show again later. And what's nice about this work is that we're actually going to be probing all of these degrees of freedom. That's described here by these nice little magnifying glasses. So I'm going to give a very basic overview of 2D materials and magnets. So why do we want to study 2D magnets? Well, it's an extension of studying ferromagnets in the time domain. For about 25 years now, it's been known that when we photo excite a ferromagnet, specifically a metallic ferromagnet, it demagnetizes extremely fast, much faster than previously anticipated, and on timescales that are faster than the operation of most magnetic recording media. Here I'm showing a comparison. Most hard drives work at around a nanosecond timescale. I think the fastest switching is around 250 picoseconds. I might be off now. There's probably newer work. And this is the seminal paper from 1996, where you can see this initial very fast demagnetization of metallic nickel. Now, again, 2D magnets are van der Waals materials, so we can imagine putting them on each other and introducing new kind of functionalities that were not available just with one material. I will come back to that in a minute. And the end goal of all of this is, of course, to get new applications. Here I've just shown two examples, MRAMs or read-write heads that are very common in all our hard drives. Now, why do we want to study FGT in particular, or specifically 2D magnets, as opposed to just 2D materials? Well, 2D materials in general are crystalline in such a way that they can be easily exfoliated and can remain crystalline down to a monolayer limit. And this is a side view of FGT, where you can clearly see that its unit cell, shown here, actually is composed of two different layers. And it's been shown, of course, for graphene initially, but for many other materials afterwards, that it's extremely easy to exfoliate down to a single monolayer and get different electronic functionalities. Now, in extension in 2D magnets, this is quite apparent because we have many more properties that can be manipulated just by changing this crystal structure, just by removing the amount of layers. Here I'm showing an example where you can see that the hysteresis loop of this material changes in its with the coercivity, essentially is changing as you reduce the amount of layers. Here you can see that the TC is changing. In this case, it's reducing, so no, not amazing. And FGT in particular also remains a perpendicular anisotropy system, meaning that it is useful for many applications. Well, this used to be a very big thing where people would try to induce stronger and stronger perpendicular magnetic anisotropy. So that's a bit on FGT. And I'd like to move on to talk about, actually, sorry, I'd like to say one more thing about this. This is kind of towards the vision of where we want to get to. We want to get to crystalline heterostructures, which are composed of single layers of materials tailored in such a way that we can combine the properties we want from different materials. Here, I stole this nice image from this paper over here. It's a beautiful image where we see the 2D magnet, we see a TMDC, and we see graphene, each giving their own contribution to a sort of combined device, which would be atomically thin. This thing would be on the order of a nanometer, which is revolutionary, really. So now I want to switch a bit gears and talk about why do we want to do ultrafast science in general, and specifically on this material. So if you imagine us exciting a system with a very short laser pulse, what happens is that we knock it out of equilibrium, and this allows us to then study it out of equilibrium if we are able to view it on fast enough timescales. And these timescales are typically femtosecond and picosecond timescales. So by using very fast probes, we're able to then study the system in its sort of on its intrinsic timescales before it reaches a new equilibrium. And specifically, if you imagine this kind of picture here, you can also envision that we would study how a system would evolve following a photoexcitation, and how the coupling between its different degrees of freedom would evolve, or we could study them. So what I'm showing here, to give you a bit more of an idea of picture I have in mind, is 3 heat baths that are coupled to each other. And here we have a picture where each one of the evolution of each one of them is portrayed individually. So here you have the evolution of the electrons, the lattice system, so the evolution of the phonons, and the evolution of the magnetic system. This is demagnetization, which is not in units of energy like here, but in units of angular momentum. So of course, I'm going to come back to this about now. And I want to do something a little more pedagogic, in that I will describe how at least my view of the 3 levels of understanding of such couplings. Now, the first level of understanding will be coupled thermalized baths, which I will start with now. This is more of what I've just said. And there will be 2 others. And we will then use this on FGT. So if you imagine these 3 kind of heat baths or degrees of freedom, which we can assign to a given system, we can then imagine that we dump energy into the system very fast using a fast laser pulse, and the energy will flow between these degrees of freedom in a way that we can then describe using a single number for each one of these. This would be in units of temperature or energy. And we could imagine how these temperatures change using some kind of energy flow model as shown here. This is a 3-temperature model where we have a couple differential equations that allow us to then describe how these arrows turn into these coupling constants that govern the flow of energy. I'm showing again this picture here from this very nice Koopmans paper from 2010. Right, and this gives us a lot of insight. But one thing that is clearly lacking is the understanding of what these things are actually doing within themselves. And on a more general on a more general level, we should be asking ourselves, can we even use a single number to describe the temperature of such a system? So in other words, can I, for example, imagine the electrons as being in a thermal state, or a state that I can assign the temperature to? Because one could imagine that in non-equilibrium conditions, the electron distribution cannot be described by a Fermi-Dirac distribution, and the distribution of phonons and magnons cannot be described by Bose-Einstein. Why would we assume that they can? And this brings me to the second level of understanding of such couplings, which is sort of the internal thermalization of these degrees of freedom. And so the conceptual understanding here is that there is evolution within these heat baths. So not just transfer of energy from one to the other, but also within them. So we have to break them apart. Here is a nice image taken from this paper from 2012, about 10 years ago, where we have a sort of a cartoon of how the electron system evolves following a photoexcitation. We initially have a very excited carrier population up here in nominally unoccupied states, which then cascades back down through a series of scattering events and eventually relaxes to a new thermal state. And every scattering event here, they lose energy. This energy, of course, is what is transferred to the other degrees of freedom. But this cascade in itself tells us that the heat bath, which we call the electrons or the carriers, is not in equilibrium with itself, and definitely not necessarily in a thermal state. The same can be said about the lattice and the spins. I'm only going to talk about the lattice here because I think other people can say more about the spins. But the concept is similar. Here we have the phonon dispersion of graphite from this nice paper over here. And the same thing is sort of described. Here we have an initially excited phonon population up here, and through a series of phonon-phonon scattering events, this initially highly sort of preferential occupation of high energy optical phonons evolves to lower energy phonons and eventually to a new thermal state that's characterized by a higher temperature than the temperature we started with. And if I then make this in a slightly more cartoonish fashion, which helps us to understand, I would draw something similar to this. So here we have now, I've broken down the phonons into a number of groups, where we have an initial group here that is highly coupled to the electrons. So this is electron-phonon coupling. This is, of course, a cartoon. And then we have phonon-phonon scattering events, which sort of describe how the energy flow is not only into the phonon system, but also within it. Right. So the last level of understanding is more for pedagogical, kind of the goal we want to get to. I'm not going to actually talk about this in FGT, but it kind of is intuitive to imagine that if we have something happening in the electron system, it's connected to something in the phonon system. And when I say something, I mean a specific event or a specific degree of freedom. And there's two very nice examples in recent literature that I like to describe. Here we have a paper about iron selenium that was published a few years ago, where the key observation, there's two key observations. One is using X-ray diffraction. They observed this motion of these atoms. These are selenium atoms moving up and down in a coherent fashion. This is shown here. And this, the y-axis here is this delta Z, which is in units of length. And here in a time-resolved ARPA's experiment, we have this motion of a band described by a change in energy, or delta E. What I want to get to is that if we can identify that these two things are actually moving in the same frequency, and by taking delta E over delta Z, we can actually experimentally describe the coupling between parts of these degrees of freedom, or a coupling. But I wrote coupling potential here in kind of quotation marks because maybe there's better terminology or more correct terminology. But you can immediately identify that this is in units of energy over length, which is related to a potential. And this is another example of essentially the same kind of work done in two papers, also very nice work. Right. So let's now move to talk about FGT. And I'm going to start with this kind of picture with the many degrees of freedom. So if we imagine our system, electrons, lattice, and spins, we're now going to do a bit of what I call stamp collecting, which is a very big understatement. We're going to initially look at the electrons, and we're going to see how they evolve. We're going to do this using a time-resolved ARPA's experiment. This is a conceptual description of the time-resolved ARPA's set up at the Fritz Haber Institute, where the experiment I will describe was used. And the kind of data you get out of this is very nice. It's four-dimensional, two dimensions of momentum, one energy, and time delay, which is the delay between the pump and the probe before photo emission to one of these two detectors. And this is the kind of data you get out. It's very pretty. This is, if I'm not mistaken, this is data from tungsten diselenide, a TMDC. And if we have these kind of data, the intensity that we see can be described as the product of three terms. One is the spectral function, which is what we would call a band structure in simpler terminology. The other is the Fermi-Dirac distribution, which tells us about the electron energy, which is specifically helpful if we're looking at a metallic system like FGT. FGT is metal. And this is the matrix elements, which I will not discuss. And we're specifically interested in the Fermi-Dirac distribution because it changes as we change temperature, and then we can extract the electron temperature. And this is shown here. These experiments were done by Tommaso Pincelli, who is a colleague of ours here at the Fritz Haber Institute. And what you can see here is the characteristic excitation and relaxation of the electron temperature in FGT. And we see that's about 200 femtoseconds. That's very nice. I'm not going to go into more detail. I'm going to continue in my stamp collection now. So now, after I'm done looking at electrons, I'm going to look at the spin system. And to do this, I'm going to use XMCD. So I'm not going to describe XMCD in so much detail, but you can see here, actually, this is a paper about XMCD on FGT from 2016. The key feature here is that we have two curves which represent absorption from left and right circular light. And because there's a difference between them, this difference shown here is proportional to magnetization. So this is what we're going to do. And we're going to do this in transmission geometry, which is actually the cleanest way, to my knowledge, to do this kind of experiment. So this is what our sample looks like. We use this area here, which is relatively big, 200 microns or so, a bit more even, or even smaller than that. And this area here is thin, so we can transmit through it reliably. This is actually 49 nanometers. We went to femtospecs, which is an ultrafast beamline at BESI-2, and worked together with our colleagues there to probe the system. So this is what the data initially looks like. This is our XMCD spectrum from FGT. So you can see that there's a difference here between left and right circular light, and we get the L2 and the L3 peaks as we would expect. And now we want to make sure that this is actually magnetic and behaves like FGT. So we stand here at this energy. This is 707 eV. And we watch how this contrast changes as we change the magnetic field. And this is shown here. This is not the cleanest data I'd like, but this is also not the purpose of our work. So we can clearly see a hysteresis curve, which is nice, proving to us that this is ferromagnetic. And now we stay at this energy, and we're still probing this magnetic contrast, and we shoot the system with our laser. And this is what we get. So this is now another curve showing us dynamics from FGT. And what we have here, this inset here is just a close up here because I wanted to make sure that I present the error bars because the error bars are not so small. And also the time resolution. So the time resolution here is actually very good. It's 100 femtoseconds or so. I'm pointing this out because here there is a drop, and this drop here is artificial because in this part of the image, the resolution changes to be about 50 picoseconds because this is on much longer timescales. This is now in nanoseconds, hundreds of picoseconds, and this is in single picoseconds. And so we see that the initial drop here is on the order of 200 femtoseconds, which is very similar to what we saw in the electron dynamics, which is not so surprising. Metallic ferromagnets tend to have very fast spin dynamics. We also have a longer time scale here, which I'll come back to. So the last experiment here in our FAM collection will be an ultra-fast electron diffraction experiment, shown cartoonishly here. And so what we have, if you look over here, we have a femtosecond electron pulse and a laser pulse, both exciting the sample. The electron pulse passes through in transmission. It's the same kind of sample as I just showed for XMCD. And we get a diffraction pattern as shown here. This is not a diffraction pattern from FGT. This is a diffraction pattern from FGT. And what you see here is many, many diffraction spots. Each one of them is characterized by a unique, what we call Q. It's a scattering vector, which we can describe using Miller indices, and reflects a distance in reciprocal space. So this picture is in, the distances in this picture are in units of inverse distance or momentum, if you will. And what we want to understand is what happens to these peaks. How do they change? So I'm going to initially show a quick result followed by a more detailed result, and you will understand in a minute why. So for now, I'm just showing how these peaks weaken in intensity. And this is what is shown here. This is for increasing distance from the center, and this makes a lot of sense to anybody who is familiar with this technique, because as you go away from the center, you have a stronger Debye-Waller response. Now, this picture here is not the newest analysis of these data, but everything here is qualitatively very, very correct. There's a bit more cleanup that needed to be done here. So we have these wiggles that we see here, and we have the more obvious drop on very fast timescales happening at around about a picosecond. Time zero here is a bit shifted. And so if we then look at these two observations, one is this drop and the other one is these wiggles, we get these two graphs. One of my colleagues told me that this axis might actually be a tiny bit wrong, so that happened this morning. But what I want to focus on is this. What do we see here? We see here what I call an effective mean square displacement, which I will now explain. This drop in intensity happens because our atoms spend less time at their nominal high symmetry position. And they spend less time there because they vibrate more as more energy is passed into the lattice because of a growth in phonon population. So what we see here is a description of that. This is a graph that shows us how the vibrations of the incoherent vibrations of atoms rise following the photoexcitation. And we see that we have two timescales here. Again, an initial very fast sub-picosecond timescale, similar to what we saw before, and another longer timescale. And I want to first finish our initial stamp collection and then come back to this. So what we've done is we've looked at all 3 degrees of freedom, and we've collected data from each one of them. So in principle, we can very easily apply a reliable model to describe energy flow between them, at least on a simple level. It turns out that this is not as simple as I would like. And I'm working together with 2 colleagues from Madrid, Unai Atizia and his student Theo Gripe, to use all 3 degrees of freedom to model energy flow kind of correct, what we believe is correctly. Which I think is exciting, also because I am not familiar with a lot of works where you can see all degrees of freedom at once. So that's kind of nice. And stay tuned, or making progress. This will be published soon. And now I want to go back to talking about the lattice because I like diffraction. So I want to talk a bit more about the internal thermalization of the lattice system. And part of the reason that this is very relevant to 2D magnets is because, as I showed you in the beginning, in 2D magnets, you can remove layers and you get changes, often very large changes, in magnetic properties. So you're essentially changing the lattice and you're seeing changes in magnetic properties. So understanding how the lattice relaxes would then allow us to understand what is actually coupling to the spin system. Can we manipulate the spin system using specific properties of the lattice? Can we photoexcite the system in a kind of wise way so that we control the spin lattice coupling in such a system? That's kind of the thought process behind this kind of experiment. So diffraction in general gives us Bragg peaks, like you just saw. And different things can happen to these Bragg peaks. This is an image taken from the PhD thesis of Daniela Zahn. And one of the things you can see is intensity going up and down due to a coherent phonon. I will talk about this in more detail in a minute. And like I also said before, you can also have just a decrease in intensity on all Bragg peaks because of a growth in incoherent phonon population. And you can also imagine Bragg peaks moving around because of extraction or expansion or contraction of the lattice. So if we think of our data, this is essentially the data I just showed you. One of the greatest powers of diffraction is that it is very deterministic compared to many other experiments. And what I mean by this is every single Bragg peak here its intensity can be described analytically with a structure factor like shown here. This is a sum of every ion in the unit cell. And there are 3 terms here. One of them is one I will not touch. It's just how strong every ion scatters. And typically heavier ions scatter more, lighter ions scatter less. This is true for electrons and it's true for X-rays. It's not true for neutron scattering. This is a phase factor where the positions of the ions come in, their positions within the unit cell. And here we have the temperature factor where we have the Debye-Waller effect, meaning that if an atom moves more around its high symmetry position, it reduces the overall intensity. And this is stuff from undergraduates. So if we now imagine a coherent phonon, its effect on the intensity will come in here because all of the atoms will move together like so. If you imagine a single unit cell, the atoms will move along a specific trajectory that is defined by the polarization vector of this specific coherent phonon. But we call it coherent because every single unit cell has the same motion in phase with every other unit cell. And that's why we would describe this motion in here, in the position of the ion. And these kind of oscillations would be sinusoidal and would lead to these kind of wiggles shown here. Now, energy flowing to the lattice doesn't necessarily need to lead to coherent phonons. Most of the energy produces incoherent vibrations of atoms like this. which reduce intensity. As you see, if you just have a growth in how much this atom moves around, you will have a growth in this temperature factor and therefore a reduction in intensity, which is what we see here. And because of this Q squared term, the atoms that are further away from the center reduce more. It's a Q squared inside of an exponent with a minus. It's very kind of intuitive. And so this kind of looks like this. We just have a growth in how much all of these atoms vibrate. Now this is nice, but also can be described analytically as well. So if we model these coherent phonons if we know the phonon distribution of this material, and we typically do, we can describe the coherent phonon using a term that is time dependent. It would be a sinusoidal term, and it would be different for every single ion species. So for iron 1, for germanium 1, for tellurium 1. And the incoherent oscillations of every ion species would also be described analytically. And in this case, we would need a tensor. But lucky for us, there are all sorts of symmetry restrictions on on these terms here. First of all, this is a symmetric matrix, so we only have 6 terms. And then because of the specific positions in the unit cell, we end up that every single ion can be described by one term, this UFE here. So it's just one term that is time dependent and comes into this matrix. And the same is actually the case for germanium and for tellurium, which is very convenient for us. The reason it's convenient is because we can have very few parameters. So we ask ourselves, can we systematically extract these quantities from our data? And if we have only 3 parameters describing the incoherent oscillations, and probably less than 24, which is because these are vectors per delay, we could imagine that we have 470 unique data points per delay, which is every one of these Bragg spots. So every one of these Bragg spots is described by a unique equation, which depends on only a few parameters. So we can imagine a situation where we can essentially solve the crystal structure in the time domain per delay. If we have hundreds of data points and only, 10, 20, 30 parameters, we can systematically describe all of the atomic motions in the unit cell. Now, I'm not going to show you this result for FGT yet, but we have done this on a number of similar systems, most recently and soon to be published on a TMDC monolayer. So this is a monolayer from the group of Professor Bracic in the University of Munster, done by our student Hein Young. And what you can see here is a monolayer of tungsten diselenide. This is a cartoon shown here. And you can see that the incoherent oscillations of the selenium atoms follow a different path than that of tungsten. So we have an initial rise in phonon population, which affects the vibrations of both selenium and tungsten, followed by a change in trend. There's sort of a next phase in the phonon-phonon relaxation process. When you imagine a kind of picture like this, we have an initial growth here, followed by different phonon-phonon relaxation processes here. So we know that this technique can in principle work, and that's the direction we're going towards. Again, stay tuned. So what I've shown you today is 2 things. I'm coming towards the end of this talk. One is a description, a kind of what I would call full, in quotation marks, picture of energy flow in FGT using 3 different experiments, which still remains we need to finish modeling this, and a detailed picture of phonon-phonon relaxation within this 2D magnet. And of course, the main open question that will remain even if we solve this is, how does magnetism relate to these different processes, which we could do if we would do this experiment in and out of the magnetic phase. What I'm showing you here is data taken well within the magnetic phase. And so with that, I'd like to come to an end. I'd like to thank everybody who's involved, and the CRC TRR 227 on ultrafast spin dynamics between Berlin and Halle, and you for your attention. Thank you. I think.
Thank you. Thank you very much, everybody. So I think internet is a little bit spotty, but I think it's okay. So let's say I'm going to bring, I think we have questions. Please raise your hand and I will promote you to panelist and you can ask your question. So I think, let me see who's coming up in here. Yeah, Marcos Guimeres and Massimo Alteri are coming up. So let's see, well, Marcos, why don't you, oh, Massimo, can you unmute yourself and ask your question? Okay.
Okay. Well, thank you very much for this presentation. I mean, in your general introduction in the beginning, you discussed the issue whether it makes sense to define, at all times, a temperature for one of these reservoirs, let's say the electrons, or, whether they are not in an equilibrium state, and then the temperature doesn't make much sense. But then when you showed us the results of Tommaso Pincelli, I think you had a graph where there was a definite temperature at every point in time. And does this mean then that the equilibration to a thermal distribution of the electron gas is much faster than you can measure, or what?
So this is an excellent question, and a topic of a lot of conversation and argument between people. My opinion is that this graph makes sense only from a certain point onwards. On very short time scales, typically definitely within the resolution of the experiment, it does not make so much sense to define a temperature, even if you can fit a Fermi-Dirac distribution to your data. I have not shown here any other ARPAS data on the system because this is my colleagues' work and not mine. We have reason to believe that in the relevant time domain, sort of after the initial rise of the electron temperature, we reach a new thermal state, which can be defined by a temperature reliably. I think this is kind of the answer to the question whether a temperature can be defined. It can be defined from a certain delay onwards.
Okay. Marcos, can you unmute yourself and ask your question, please?
Yeah, thank you. Some beautiful piece of work. It's very nice to see the combination of techniques. I was wondering how these results and the timescales that you get compare with ultrafast demagnetization dynamic measured by MOC and doing the analysis with the microscopic 3D temperature model that you showed also in the beginning.
So I've not measured the system in MOC.
No, I mean, how does it compare? So the timescales that you obtain and the transfer of energy that you get, how does that compare with works that measured using time result MOC and then use the microscopic 3D temperature model to analyze it?
Okay, so I cannot compare. So what I can do, I can compare to other systems. There are other metallic systems. I'm not familiar with, I'm sure somebody's done a MOC experiment on this material, but I have not seen a publication. There's probably something in the archive by now or maybe published recently. But I cannot compare to a MOC experiment on this material. However, this material is a magnet, and it's a ferromagnet, and it's metallic. If I compare to other metallic ferromagnets, where I believe we have itinerant spins, the timescales are extremely similar to the extent that this material demagnetizes in an initial phase of about 300 femtoseconds, which is very similar to nickel. It's a bit faster than metallic iron. I don't have much to say about this. What is maybe different than these materials is that it is a type 2 demagnetization, if that means something to anybody here, where you have an initial fast drop in a magnetization followed by a much slower one, which is typically assigned to a situation where you have the initial relaxation of the electron system is sort of over. So you don't have much less of phase space for scattering off of carriers. And then all of your demagnetization sort of slows down. This is very apparent mostly in lanthanides, where you just have a very large moment to demagnetize, like 10 μ or so, or something like this, 7, whatever. But there has been a nice work that showed that under certain conditions, you can force even a simple ferromagnet like nickel to become type 2. So this argument of kind of the end of the relaxation of the carrier system, to me, seems kind of vague and not well described in literature, but has been mentioned several times by now. So we're going with it. I guess that's the end of my answer.
Okay, great. Are you, by the way, trying to show some slides or not? I'm not sure.
No.
Because the slides is okay, good. That's to be clear. So Steve, go ahead and unmute yourself and ask your question.
Yeah, so yeah, thanks for the nice talk, Will. I guess I have a comment / question. So one is regarding the electron diffraction results. I think I guess as you're probably aware, there is a little bit of a difficulty in making a one-to-one assignment between RMS displacement and energy or phonon population, because particularly in a non-thermal state, those are not really simply related. And so I guess the related question would be, what is the average acoustic phonon period in that system, and how does it compare to this 0.3 picosecond timescale that you observe?
So let me start by answering your comment in the beginning, which I think is very relevant. There is a difficulty going from these kind of mean square displacements to something that is in a more convenient picture, like a phonon picture or an energy picture. That would kind of convert to temperature. But we kind of don't need to use that picture. If we keep to mean square displacement, that is something that does not depend on whether the system is in a thermal state or not. So there is a certain advantage compared to, for example, ARPES. In ARPES, if we extract a temperature, we're then worried, is this temperature actually meaningful or not? However, in a diffraction experiment, we can extract the mean square displacement at any time delay, and it is a meaningful quantity regardless of whether the phonon system is thermal or not. It's what's not trivial is then to say, okay, can I take this mean square displacement or all of the mean square displacements in the system and convert them into that phonon picture? That's not easy or not trivial, and definitely not a one-to-one conversion to temperature. Your question about the mean acoustic phonon, what was it? The phonon amplitude? I'm sorry, it was long.
The period. So like there's a dynamic limit to how fast you can see changes in the mean square displacement. That's essentially half the average acoustic phonon period. And I'm wondering how close you are to that with this 0.3 picoseconds.
Well, why do you limit this to an acoustic phonon? I mean,
because acoustic phonons are the lowest frequency phonons in general. I don't, maybe in these layered systems, there might be some interlayer modes that are slow. Usually they tend to dominate the mean square displacement because they're lower frequency. That's why.
I see your point, and yes, acoustic phonons tend to dominate this. This is an absolutely excellent point. You might have been a referee of ours at some point, of mine. Nobody knows. I actually don't know. I don't know what the mean is, but that's a good point to take home. Thank you.
Okay. Okay.
Actually, there's no way you were.
So let's go. Thank you, Steve. No, it's okay. Better not to guess. So Sasha. Alexandra, go ahead and unmute yourself and ask your question.
Yes, yeah, thank you for a very interesting talk. I have maybe a bit naive question about one of the last plots that you showed about this TMD dynamics. So to understand correctly that on the time scale which you studied, you cannot really say that all the ions are kind of thermalized with each other. So my question is like, what is the real thermalization time for the lattice then in this?
You're talking about this?
In this one, yeah.
What is your question? What is the thermalization time of a lattice?
Yeah, like from your data, what would you?
Much longer than this. I'm showing the initial time frame here. This goes on for tens of picoseconds.
Oh, okay, thank you.
Especially in semiconductors, we often see that the lattice doesn't actually thermalize, or at least remains in some non-thermal state, often for several tens of picoseconds.
Okay, thank you.
Sebastian, go ahead and unmute yourself and ask a question.
Thank you for this really nice talk. I have a question about your slide 33. Excellent. So here on the left-hand side, near the lattice heat bath, you have this plot. You were just answering a question, exactly, a question about this. So this is what you call the mean square displacement. I just want to clarify. So you are not saying that this is related to the Debye-Waller factors? Or so, you are?
I am, but
okay.
This is a, so what we're seeing here is an average. In order to be able to simply relate, this is why I kept the initial description of this kind of a heat bath kind of picture separate from this. This is sort of a semi-wisely weighted average of the response from different Bragg reflections that gives a reliable picture of how fast the lattice responds. One could argue that it's not reliable enough. That's why we would then have this description. And it essentially, it simplifies the system in kind of saying, okay, let's just assume the unit cell reacts as a whole, Debye-Waller style. We get a reduction from the whole unit cell, and this can be described with such a curve. That is essentially what we're saying. So it is, in essence, of the Debye-Waller picture, but not to the detail that Debye-Waller typically has when you assign a specific Debye-Waller factor for every ion in the unit cell.
Thank you.
Okay, and I think this is one comment that I wanted to read from that. I think that there's a suggestion that I guess squid can be used for this relaxation experiments that Faisal Zeb wrote in the chat. That, and then, oh, sorry, there's a question from Alex. Sorry about that. Let me promote him so he can ask a question himself. Let's see. I think he'll come in a second.
Comment in the chat.
He's in the chat. It's actually in the Q&A. He's actually, but usually I try to.
Okay.
I thought they would join us panelists, but I was not quick enough to put that out there. No, so Massimo, do you still have another question that you wanted to ask in the meantime? Your hand is still up.
Yes,
so
yes,
sure.
if I may.
Yeah, go ahead.
I'm curious. I mean, if I understood correctly, this system, monolayer system, is a ferromagnet, which means it breaks time reversal symmetry. Now, when you have a 2D system that breaks, say, either inversion symmetry or time reversal symmetry and so on, there are normally, one can expect a pronounced Berry curvature effects. Are any such effects been relevant in this system?
Interesting question. I'm going to answer that I don't see how this is directly relevant to most of what I've talked about, in the sense that where would you gain a Berry curvature? You gain it, well, you gain a Berry phase when you move from one quantum state to another. The Berry curvature can be an analog to a magnetic field in reciprocal space, right? Or in some phase space. Now, where would this affect this experiment? I don't immediately see, so I cannot really comment in a smart way?
I think, if I may,
I can comment on that.
the evidence is that in other systems, at least, is that this could alter the interpretation of your XMCD experiments.
Mm-hmm.
As you know, the connection between XMCD sum rules and say the orbital moment and so on, they could have additional terms which are connected to the Berry curvature.
You're talking about the quadrupole
Actually,
moment?
let me No. He's actually talking about the dipole moment, but it's actually the same thing. So maybe I can comment, Massive, also, since that's something that I'm a bit of an expert on, on anomalous Hall effect. So essentially, the Berry's curvature and connected to anomalous Hall effect and XMCD, which essentially is the X-ray version or the finite frequency version of anomalous Hall effect. By symmetry is allowed, essentially, because you have an axial vector allowed in your system, because you have magnetization, you will have a response on the XMCD as well as anomalous Hall effect in DC transport. Now, you can write, if most of the effects are coming from interband transitions without a strong contribution from side time scattering, which tend to be only a small correction, or skew scattering, which tends to be for very, very high conductivities, in the DC limit, that's going to be connected to this Berry's curvature integrated with the whole phase space, which can be translated to these interband transitions with these dipole matrix elements. Now, once you go to finite frequency, essentially you're modifying your denominator. Instead of dividing by the difference in energy, your difference in energy plus the frequency that you actually involved in the transition, but it's still connected in that sense. Many people call it Berry, but in reality, you don't have to ever say Berry curvature if you just do the calculation from the Kubo formula in reality. So in this case, the fact that he's seeing XMCD, that is a connection that you have a finite Berry's curvature in the DC limit. So essentially, that's the fact that you have an XMCD experiment that is non-zero. That is an evidence that you have, you can call it Berry's phase if you like, a momentum space. There's different parts of it. What is not so clear is how the bands cross near the Fermi surface, because this is when whether you have a strong anomalous Hall effect or not comes into play. But that's really where that, with these large Berry's curvatures tend to be, when you integrate them, tend to be large when this crosses near the Fermi surface. And that's one has to look at the band structure, and that's all. Yeah. But in the XMCD, the fact that you have XMCD being observed, that's really evidence of those physics. Yeah. So Massimo, did that help answer your question?
Yeah, thanks.
And then I think we had one last question from Alex Hamel. Do you want to?
Yeah, sure. Thanks. Yeah, and thank you for the
answered your question in the Q&A.
Oh, you did? Let me see. Oh, I'm not. Let me see. Answered. So I think that was a different question in the Q&A by Evan Suresh, talking about spinor charge current. Mine was something different.
Yeah, I answered this lovely question. Okay, yes, please continue.
Yeah, so I just know from my own work, in terms of looking at magnon-magnon interactions, it is highly dependent on the frequencies and wave vectors of the magnons involved. And so I was just trying to map that to my understanding of your work from this presentation. So, and I might have just missed where you talked about like the wave vector resolution, but is it that for each phonon mode you're looking at, for example, its effective coupling to the entire electron bath, or was it, or am I kind of just missing your approach?
So this experiment is not done with wave vector resolution. We're not looking at specific phonons. In essence, we're not limited, quote unquote, to the phonon picture, in the sense that what we extract from a diffraction experiment is a quantity that tells us how much the atoms are vibrating. Now, different atoms vibrate differently at different temperatures. This just is a completely static description. It comes out of when you solve the crystal structure using neutron scattering or so, you get a Debye-Wohler factor, which then tells you how much your mean square displacement is for that specific temperature. Now, this can then be mapped onto the phonon population, but we do not directly probe specific phonon modes unless we have a specific situation where we have the kind of beating of a coherent phonon, which was apparent here in this. I don't know if you can still see my mouse. There's a coherent beating which comes about because there is a specific phonon mode at the gamma point that remains populated for, I don't know, several picoseconds over a large, over a wide area in the sample. So it remains in phase. But this is a kind of specific case, which is relatively common in these time-resolved experiments, because this kind of exotic scenario of a coherent phonon is quite easily visible in many ultrafast experiments. So this is often discussed, and also it's a useful thing. Does this answer your question?
Yeah, it does. Thank you.
Yeah. So one last question. I think Igor has one last question, and then we'll stop with there. Igor, go ahead.
Okay, thank you. I think it's maybe more comment than question. The matter is that both notion of phonons and measurements of electrons interpretation are based on assumption that when you distort system on such a short time, bands still exist and phonons have time to be formed. So screening of electrons provides you existence of phonons, because before that it is just oscillations of nuclei which are not screened, right? You need time, electrons need time to screen these oscillations, and then you come to phonons, right?
I see what you're saying.
Yeah, and then bands themselves, when you excite system, all bands are not relevant. And this means that it's very difficult to interpret this data in terms of this formula, which contains first Fermi-Dirac function, which actually should enter as averaged with width of these bands and the Bayer-Wöhler factor, which also it's not clear why this exponential function should appear there. So actually, your data on the slide 33 needs more theoretical attention. That was my comment. That's it.
Thank you for your comment.
Okay, great. Good point taken. So with that, I would like to, there was 120 of you today that showed up, and there's quite a few that stayed even for the long Q&A session that Will so generously gave his time for. So I'd like to thank, I'm going to stop the streaming now. Let me hang on a second. I'm going to end the streaming. And thank you all for